All right, so let's try now discussing 2 qubits. For the 2 qubits, I need the slides again. Okay. So there's just one comment I want to give. 1 qubit is boring because I can simulate it now in Qibo, yeah? 10 qubits I can also simulate, but they are challenging in the lab. It's already fun. And if you see ever 100 clean qubits, then it's really worth the buzz, okay? Before that, we are still developing the technology on the physics, engineering, kind of hardware level, okay? It's experimental work that needs to be done. But okay, let's assume we have now more qubits and see how we can work with them. So for example, let's say we want to have 2 separated qubits far away from each other in the lab, and we want to turn them into 2 plus states. So we will, this is depicted with the circuit here. Those are 2 separate qubit rotations, but the way it is modeled is using the Kronecker product. So here I'm also showing the Wikipedia page. That's actually one of my favorite Wikipedia pages. It's very useful. This is really worth going through the definition here, okay? So we will be using now this Kronecker product in NumPy as well. And then later we will go to entanglement. Okay, I will show this in a second. So 2 qubits. So we use our conventions next circuit, then we say circuit capitalized, but now we change something. We say it will be 2 qubits in that circuit. And in circuit number 4, we add a gate from gates, and that will be a Hadamard on the first qubit. And then I just copy paste this, and I do the same thing on the first qubit, okay? And now I need an initial state. So let's say I will have a plus state, and then Kronecker product plus. And then the Kronecker product, that's why we have NumPy all the time running in the background, is just, okay. So let me call it somehow differently. It's actually, I meant to do cat 0 and then twice. So this will be my starting point, and plus O plus. My candidate here will be circuit number 4 applied to this cat 0 and tensor power 2. Okay. So if I run this while it's running, I just want to tell you this definition of the tensor product. You have 2 boxes here, 2 operators applied to 2 receiving boxes states, which means it's the 2 states that are modified by those operators individually. That's how tensor products act. So for example, if we apply the tensor product of Hadamards to those zeros, the first Hadamard gives me a plus, the second also, and then I tensor it, okay? And then if you want to do some homework, think about this problem. What kind of operations could you do such that you can test that this is an eigenstate? So you can try to use this again with the norm, but applying some probing operations to check that they are really eigenstates of X, for example, and verify that, for example, we really got a plus tensor plus operation. This will lead you to start thinking about how to do it when you will have n plus states, what would be happening if you don't have this product state structure, and it's really leading you towards some questions that are fundamental to the problems we are tackling in theory of quantum computers, verifying, certifying, and so on. It's like the smallest entry point to see there's trouble ahead, and that's why I was showing those many states as the state space is growing. Okay, I don't intend to show you why exactly the circuit for preparing the Bell state works the way it works. Okay, but I will show you how to implement it in Qibo. That's fairly simple. So what I want to tell you is that that if we start from 2 cat zeros, the way we prepared them just now, apply a Hadamard to one of them, And then we have a new operation called C0. It's one of the most fundamental operations in quantum information. Then as the output, we should get the state. This is called the Bell state, okay? A Bell state is basically the most fundamental state for entanglement, and entanglement is a physical effect. There was a Nobel Prize for exactly studying with experiments this new physical effect called entanglement. And the Bell state already features essentially all of the fundamental aspects of entanglement, which is basically a new type of correlation that comes from quantum mechanics. Classically, you might have correlations that you might think of using classical coins and so on, but Bell states are kind of the root of understanding entanglement, a new type of correlations, quantum correlations. Okay, so I'm not explaining exactly what's going on. It's just for us, it's now this state. The point is that we will have a circuit in Qibo. If you have remote access to hardware, you could prepare that entangled state physically on quantum hardware. So that's all that I have to say here. And one other thing is that if you study a physically entangled state in the lab, then basically you can ask how entangled it is in terms of thinking about those Bell states as well. So it's really the states to think about if you want to think about entanglement. So now Hadamard and this we know. Okay, this we know. Check. And C0 is this one. You will often see C0 written as a 4x4 matrix because this is a 2x2 matrix. This is the identity on 2 qubits. This is a 2-level identity, 2-level Pauli X operator. So it's a 4x4 matrix, but this is telling you what's going on really physically. Basically, this dot is telling you that we are checking whether the incoming first qubit here is in 0 or 1. If it's in 0, apply identity to the second qubit. And if it's in 1, flip the second qubit. That's the C0, okay? And this is really the way of understanding those C0s, CZ operators, and so on. Those controlled operators have a flag qubit here. This control qubit is like a flag, and this flag is switching the operation we apply. Okay, so that's our C0. And really, you could convert this to a matrix yourself, but we don't have to do that because we have it already in Qibo. Okay, so we will need another circuit on 2 qubits. So this is circuit number 5, if I'm not mistaken. Circuit capitalized applied to 2. Circuit number 5, we add what we already know and did many times. X at 0, no. H. And I might have the numbering wrong. No, 5. Okay, let's keep it at 5. Okay, I apply the Hadamard. And then I need to do something new. Number 5, add gates. And then I need to do something new. C0, it's called 0 and 1. And that's our operation there. And then the Bell state, circuit number 5, applied to get 0 to, okay, that's the name. Okay, I run this. And then I can print the Bell state. Nothing will change because I was running the notebook already before. But if I print it, I will get our output here. And I could also try to multiply it. I think like this will also work. Just to show you again, this is 1, 0 imaginary part. Okay, when it's converted to NumPy, it's a 4x4 matrix, so maybe not so nice. But we saw this 0,7 factor before, which is 1 over square root 2. Okay, so this is how we prepare a Bell state in the lab. And here you have also a little bit of things to think about, so you can add your own cells and maybe try other things. Okay, thank you.